Welcome to a case study of gauge variation. Why you should have paid attention in math class. This case study will demonstrate how you can take advantage of modern measurement tools to detect problems that are not obvious when inspecting film extrusion lines. I will then review options to deal with the root causes of these problems. The way we're going to do this is I'm going to describe symptoms exhibited on a particular blown film line. And then I'm going to demonstrate the techniques that I use to analyze the root causes of gauge variation. To do this, I'm going to compare the test results from both mechanical and capacitance gauge profilers and highlight how using both techniques can detect poor mixing that contributes to large gauge variation. I'm then going to review short and long-term strategies to minimize gauge variation. First of all, some background. The film line I'm going to look at is a 2.5-inch extruder with a specific output of 2.5 pounds per hour per RPM. It's pumping 145 pounds an hour at 125 RPM. I've included metric units for those who are more comfortable using metric units. One of the reasons I thought the output was so low to begin with is because of the die. The die is relatively small at 7 inches, 180 millimeters. It was a non-IBC die, stationary, with a dual lip airing, and the airing temperature was 80 degrees Fahrenheit. So they weren't using chilled air. It was a warm day in the factory. The ambient air temperature was 88 degrees Fahrenheit at the airing and 106 degrees Fahrenheit at the haul-off nip. This wasn't the tallest line in the facility, and I was doing audit for all production lines in that facility. The temperature at the top of the tallest one was about 130 Fahrenheit. It was so hot, it actually forced my iPhone to shut down. I had to come downstairs and let it cool off before I could go up and continue to take pictures and videos and analyze what was going on the other lines. Getting back to this line, the die-specific output rate was 5.8 pounds per inch of die circumference, which is quite low for a dual lip airing. And it was running a blend of low-density linear low, mostly linear low, but a lot of low density in there. And there was a lot of yellow pigment master batch in there. These were the readings that were reported by the temperature controllers. So the reported values and the target values were quite close, and it looks like they were using a gradually increasing temperature profile and cooling off in the die a little bit, which is not the best thing to do anyways if you want to minimize your temperature variation, especially since it was a bottom-fed die. When I took a look at the film line, first of all with my camera, take a look at the picture on the left, you could see that there was a tilted frost line. On the right is a picture I took with an infrared camera. This is an attachment that I purchased for my iPhone. You can buy them for Android models and Apple models. It was a FLIR One Pro. The interesting thing about this system is that it overlays an infrared image on top of a kind of like skeletal view of what you're looking at. So it's easier to understand what you're looking at. So you could see that, yeah, there was a slightly tilted frost line, and we're going to deal with that. But the other thing that was kind of interesting is that the frost line was actually quite high. And that's not surprising considering the fact that the air temperature was so hot and it was so hot in the factory. There's two models of FLIR Ones. There's the FLIR One and the FLIR One Pro. The FLIR One Pro allows you to discern temperature variations in hot steel, not just plastics. So that's the one that I got. And the other issue about this line is that it was relatively close to the production wall, the exterior wall of the building, about 6 feet, 1.5 meters away. And that did have an effect on air currents. I walked around and took several pictures with the infrared attachment to the camera. The picture on the left is just an example of examining the die. And what I was looking for was there any unusual hot spots or cold spots on the die? And it was even all the way around. The rotator indicates that the die is capable of rotating, but it was not rotating during this audit. On the right-hand side, you've got a picture of the lay flat going through the winder. A couple of things to notice. The fixed bowed roller is there to try to compensate for the high frost line, thin on one side, thick on the other side. But you'll also notice that there are diagonal wrinkles over here, and they were pretty steady. They weren't moving, coming and disappearing, coming and going kind of thing. And typically you'll see this when you've got rollers which are misaligned along a web path. That's the biggest cause of this problem. If they are coming and going, that's usually an indication of either a web tension pulse or wobbling rollers. That wasn't the case over here. And the other example where you're going to have wrinkles coming and going is if the bubble was not stable, so it's swaying from side to side. And this was a very big stable bubble, so that wasn't happening. Now let's take a look at some of the bad news indicators from the infrared camera. First one I want to point out to you is the fact that barrel zone number 1, the feed throat's over here, barrel zone number 1 is really hot. It wasn't detected or reported in the temperature control system. The other thing to notice is that the temperature of the heat exchange, the screen changer, was much hotter than, for example, the die, which also was not reported. These are symptoms of a worn screw. Before we get into measuring gauge, I just want to go over a few points. When we measure transverse direction gauge, we're measuring around the bubble, and that's like around this band over here. You can do it at different places, but for the sake of this case study, we only did it once. One sample, kept measuring it over and over again because, frankly, I couldn't believe the results. We weren't doing machine direction, and I didn't expect anything to happen there because I watched the bubble for quite a long time, and I didn't see that frost line moving up and down. So we're going to focus on transverse direction gauge variation here. Let's talk about some of the components in a caliper that is used to measure gauge variation. We've got the guiding cylinder, we've got a supporting rod which holds a foot, and that foot settles down on top of an anvil. A couple of things to remember. This foot is supposed to be parallel to that anvil. It's not always the case. In fact, it is rarely perfect. The supporting rod, if it starts to bend for any reason, or the cylinder for some reason starts to distort, it's going to stick. You'll know that. What you won't necessarily realize is that clearance between the foot and the anvil may not be the same everywhere. And that's one of the reasons why, if it's for some reason off, you'll have one caliper which is measuring a certain film thickness. You take the same sample over to another caliper and you get a different film thickness. So in order to minimize this, we actually measure this parallelism. The way we do it is with a parallelism wire on all 4 quadrants, and we measure it about 1/8 of an inch in, 3 millimeters in from the edge if we can. This is one of the 2 instruments that I used in this case study. This is an MX1210 from Oakland Instrument. It's one of the best mechanical gauge profilers on the market. I adjusted the spacing between the samples at the shortest spacing possible, which was 1/2 inch. These are the test standards that it is qualified for. So foot diameter was as small as I could get, which was 4.75 millimeter or 0.187 inches in diameter. Foot parallelism error, that's left, right, front, back, was less than 0.04 mils. And that's 1 micron. The measurement accuracy with this device is 0.01 mils, and the measurement resolution is plus or minus 0.02 mils. One of the things that it has that's really a very convenient feature is a 3-point parallelism adjustable anvil. So as the foot starts to wear, the anvil is hardened. It's not going to wear out. And the foot is designed to be unscrewed and replaced if it gets severely worn. You can level this thing for slight wear in the foot. This is the other model of gauge profiler I used. It's the top of the line Oakland CX1025. In fact, this is the instrument from my lab. And a couple of things. First of all, it does have a micrometer on it that's just as accurate as the one in the previous model. Same foot size, same resolution, all that kind of thing. And of course, it qualifies for the same kind of methodology. In fact, you can run this, if you want, just as a mechanical profiler. The reason why it's installed here is it's a patent from Oakland. So what they do is they measure here, and it gets moved underneath the capacitance sensor over here and calibrates the capacitance sensor. The reason the capacitance sensor requires calibration is because it's an indirect measurement device, and it's based on the dielectric constant of the film. So what it does is it will measure without just an airspace here and with a film sample in here, take a look at the difference, and then calculate the thickness based on that. The nip speed is adjustable, maximum about 12 inches a minute, 300 millimeters per minute. I set it for 250, 10 inches per minute. And that's the new ASTM test method, which refers to capacitance type gauge profiling. A couple of things to notice. When you use a capacitance sensor, you're going to get 10 times the accuracy of a mechanical caliper, a high-end mechanical caliper. You're going to get 10 times the quantity of measurements. Well, I'll show you that in a second. And the measurement width is much narrower, typically about 10% of mechanical calipers. Essentially, it's the width of a bread knife, 0.4 millimeters. Here are the results when measuring with the mechanical gauge profiler. I was taking measurements a quarter inch apart, so I was able to get 153 measurements here. Target was 3.5 mil. Average was slightly more, 2% more. High, 18% above, and low, almost 12%, a little more than 12% below the target. This is not surprising with the film that, when we look at the bubble, and you can see the low spot here, that's where the frost line was higher. Compare that to what we saw when I measured it with a capacitance gauge profiler. Of course, I calibrated the profiler first. A couple of things. This is how you measure the range. It's the peak to the valley here, the lowest valley here. And what I found was, first of all, almost 10 times as many measurements. So there's 1,774 in the same sample. Average was slightly more, 6 as opposed to 2% above average. But take a look at the high and the low. High, 137. Low, almost 14% below the target. The low didn't change that much, but the high, that was much more dramatic. And my first reaction when I saw that is, there's something going on here. So just to highlight, this region over here and this region over here were high peaks that were not detected with the mechanical profiler. So you can see the numbers as a result. That was a surprise. So what I did then is I said, did I do something wrong? And first of all, I asked myself, okay, am I calibrating this thing correctly, the capacitance gauge profiler? Because the key assumption we make with a capacitance gauge profiler is that the dielectric constant of the sample doesn't change significantly through all the measurements that we're taking. But what if it does? Such as if we have a large variation in the amount of pigment in the transverse direction. So the first thing I did was confirm that the foot pressure was in fact correct, 12 psi, which is appropriate for this kind of thing. The mechanical profiler uses a mechanical system to counterbalance the weight inside, and it's a fixed pressure, and you specify that according to the test method that you can use, and that's how it arrives from the factory. With the capacitance gauge profiler, that caliper is adjusted, foot pressure is adjusted with pressure, air pressure, compressed air. So you can adjust it, and I just made sure it was appropriate. So the other thing I did was to say, okay, if there's a variation in thickness, then that's not detectable with the mechanical one. Maybe it's because there's a difference in the dielectric constant. So I went back to the region of the film where it was fairly even, not much of a change, and that's where I did my calibration using what we call multiple point calibration, so 3 points. And what I did was I just indexed it an inch, measured, indexed it an inch, indexed it an inch, measured it again, and then calibrated those 3 points with the capacitance sensor and then took an average. Actually, it was 2 inches apart. So let's compare the two side by side. This is the mechanical one. This is the capacitance one. And you'll see in these regions here, there are peaks that, well, frankly, shouldn't be there. And the peaks indicate a higher concentration of yellow pigment. That's why this is happening. One of the other nice features about a capacitance gauge profiler, such as Oakland's brand, is that it has some interesting mathematical tools in it, such as Fourier series analysis. Now, the way this works is that by overlaying different sine waves, different frequencies, different amplitudes, one on top of the other, what you can do is you can simulate any kind of wave or pattern. And when you crunch the numbers and do the math and go backwards, you get something that looks like this. So this is the Fourier series graph, analysis graph, for the mechanical sample, the one which was more believable in terms of highs and lows. A couple of things I want you to see here. First of all, the column here represents, the vertical scale represents the total impact on all the gauge variation that was observed. So one time around the bubble, you have something which contributes about 23% to the total gauge variation. Well, that's the tilted frost line. The numbers that you see here represent equally spaced impacts around the bubble. When you take a look at that, then some interesting things happen. So number 2 over here is the next highest, and that's basically too much drag in the collapsing frame. It was a very hot day. And the rest, it really depends on what it could be, and that's where your detective work comes in, to try to figure out where all these contributions are coming from. And as you start working at minimizing these things, your average gauge variation comes down, and your plot starts to become much more even all the way across. All the bars start to become the same height. Let's review what we know so far. There's a significant port line issue in this sample. The screw is running at almost maximum RPM, yet the output is well below what can be expected, even if you take into account the hot air in the factory and in the airing. There's an overheating zone number 1 in the extruder, and the screen changer is much hotter than the die. The temperature controllers don't even see this problem. These are classic symptoms of a worn screw. Well, the company didn't have a spare screw, so we needed to come up with other options. I call these workarounds, until they could either rebuild or replace the screw. And one of the most effective strategies is using temperature profiles to your advantage. There's 4 different types of strategies for temperature profiles, and that's the reason I call this slide, who's the boss? Is it the operator or is it the extruder? In other words, are you going to let the extruder do what it wants to do, or are you going to try to adjust for that? In order to do that, you have to understand where plastic starts to melt in the barrel, when it's completed its melting, and how much time there is for it to melt, and if there's any overheating, how are you going to deal with it? So if you consider what happens in the way you set up typical extruders, the feed section is where what we're trying to do is compress the pellets together, squeeze out the air. We're not melting, so there's a lot of torque and resistance in that area, and that's why by tuning the temperature properly, the load of the extruder motor is going to go up. Of course, you don't want it to go up so high it's going to trip the motor, and you don't want it to go so high that it starts to overheat and melt the material in the in either the feed throat or zone number 1. Remember, conduction of very hot metal towards the feed throat from zone number 1 can cause bridging as well. In the transition zone, that's where we set the barrel temperatures to minimize melt temperature variation at the die. And that's where your skill comes in. You have to understand what the extruder is telling you and how to deal with it. In the metering section, we normally set the barrel temperature close to the manufacturer's suggested melt temperature for that resin. If you have a formulation with more than one material, do a weighted average of the different materials. That'll give you an idea of where to start. This is an example of a gradually increasing temperature profile. The green represents the bulk temperature of the plastic. The red represents the barrel zone temperatures. Normally when extruder screws are cut, the designer is assuming that you're going to be using a gradually increasing temperature profile because that's what extruders typically like to do. Now, assuming the screw is in good condition and is designed to process this formulation, this is what's going to happen. Typically zone 1, you try to keep it cool enough so that we don't get bridging there. And we have to worry about, groove feed throat extruders that may overheat as well. In this particular case, I had recommended they move to a humped temperature profile, and that's hottest in the center. Hotter in the transition zone to compensate for less friction because what's happening is you're starting to melt, and what you need to do is make sure that there's enough friction there to complete the melting process, and as a result, you can get decent output. We always typically keep the last zone of the extruder slightly colder than the melt. And if you remember in the temperature profile, well, you're going to see it, they set the die temperature 10 degrees lower than the screen changer, which is not what I would do. Typically, I'll keep the temperature of everything after the extruder at whatever I think the melt temperature is. And if you don't have a melt temperature probe, in this case they didn't have one that worked, I add at least 20 degrees Fahrenheit to whatever the last zone temperature is, assuming it's going on and off at a regular spacing. In this case, I set it up so it's going to be more on cool than on heat. So take a look. This is what the indicators were saying. This is what it was set for. You can see how they drop it over here, which is a no-no because especially in a bottom-fed die, what it does is it chills the bottom of the die, which causes more of a spiked gauge frost line. In fact, if there were no color in there, I bet if you counted the number of peaks, it would be equal to the die diameter in inches because that die probably has 7 or 8 spirals. It's pretty much 1 spiral per inch of die diameter for a non-IBC die. So yes, I did drop the top zone, but the bottom zone, I'm going to keep it at whatever the melt temperature is. That's my target melt temperature. And I'm trying to get it as close to that as possible. So just to review, in this tutorial, what I've done is I've discussed what tools I find are useful when evaluating the performance of film lines. I've included the fact that I use a cell phone to take pictures and videos, an infrared camera attachment to find unusual temperature variations where there shouldn't be, and good quality gauge profilers to measure gauge variation accurately. The capacitance gauge profiler was able to identify the fact that there is a very high concentration of pigment where there shouldn't be, and that was a clear indication of port lines. The film was so thick that you wouldn't have known because they weren't going to be tearing the film. It was really 3.5 mil. It's pretty tough stuff. The Fourier series analysis is useful to identify contributions to gauge variation in equal repeats around the bubble, and you can use that to start working on, okay, what am I going to try to fix first? I also mentioned that looking at extruder temperature profiles is an important tool to improve both quality and output and workarounds when you have severe problems. And just one last point. When I walk into a factory and I see that the same temperature profile is used on all the extrusion lines, I conclude that they're letting the extruder be the boss, not the operator. If you If you want to find out more useful tips on how to fix common problems in both blown and cast film extrusion, I invite you to contact me via email. There are 2 books available. One of them is strictly on blown film extrusion. The summary troubleshooting guide is about 50 pages. This one is blown and cast. It's about 75 pages, and it's broken down into ugly looking film, ugly looking rolls. I can't control the process. Send me an email. I'll send you a summary preview, and then you can decide whether the book is of interest to you. Thank you very much for your time and interest, and I invite you to ask questions.